All right. Good morning, ladies and gentlemen. We're going to go ahead and go over your bell ringer now. Please remember that if you have any missing work, like the assignments that I sent out in the message to the whole class that I'm going to be putting a grade in for, you still need to make sure you make those up. So anytime you miss school, whether it's in class or virtual, you're still responsible for making the work up. So you guys have some time to do that. I haven't put the grade into this class yet, but I will be putting it in eventually. And I sent a message out through Schoology describing what's going to be included in that classwork grade. So let's take a look at today's bell ringer. And let's see what you guys came up with. So this is a USA test prep question, so kind of ACT practice. Tells us that Curious Carl designed an experiment to test the effects of ionic and covalent solutes on the freezing point of water. He hypothesized that the more solute added to a specific amount of water, the lower the freezing point. Carl assumed the hypothesis to be true for both ionic and covalent solutes. Carl conducted repeated trials and then recorded the average freezing point for each solute at varying concentrations known as molarities. According to Carl's data, what trend is evident? So let's take a look at this before we move on. First of all, you see this column here is molarity. That means the amount of solute that's added. So you go from 1 to 2.5. So clearly you've had an increase in the amount that's been added. Then we have two different examples. The first is sodium chloride. This is an ionic compound. You guys learned about that last quarter. And this is a covalent compound. And we know that because, well, everything in here are what we call nonmetals: carbon, hydrogen, oxygen, hydrogen. So now that we've established what these are, this is the ionic with NaCl, and this is the covalent. Let's look at what happens to the freezing point. The freezing point drops or gets lower. So the more solute that's added to the solution, the more the freezing point drops, meaning it takes more energy in a lower, or the removal of more energy in a lower temperature for these solutions to freeze. So let's see what options best fit the scenario. A, covalent solutes do not influence freezing point. Clearly that's not true, because what can we observe here? Well, the freezing point does change when you add more volume. Let's look at B. The freezing point decreases as the amount of solute increases. Well, that is part of what we observed here, right? As molarity increased, so did freezing point for this one and this one here. So B could be a possible response. Let's check C. There is no trend between the freezing point and the amount of solute. Well, clearly that's not true. We can see that here, because as you increase it, both sodium chloride and this compound here have a difference in their freezing point. And then D, the freezing point decreases only as the amount of ionic solutes increases. We can also eliminate D because both of these, the sodium chloride, which is ionic, and this one over here, which is covalent, follows the same trend. So they both have a decrease in the freezing point as solute increases. So that means that B is the best, most reasonable option and response for this question. So the answer is B, the freezing point decreases as the amount of solute increases. So if you didn't get this one right, you can go ahead and go back into the post and make your correction. And then we'll get ready to move on to the next activity that we're going to do today. All right. So let's transition back into this folder here. And we're going to swap things up a little bit. So we are going to do a virtual lab today. In-class students did something a little different. They did a magnet lab. Today, you guys are going to do a virtual lab using springs to represent potential and kinetic energy. I've tried to make sure that these folders are all available in the other classes. If not, I'll go back in and check, all right? So before we get started, I'm going to go ahead and share this video with you. So let me change my sharing technique here so you can see. All right, so let's take a look at the video here before we move on to the virtual lab.
Energy is not easy to define. Things have energy, but you can't hold a bushel of energy in your hands. You can see what it does, but you can't see it directly. There are different types of energy, but the differences between them are manifested only in how they make stuff behave. We do know that the total amount of all the different types of energy in the universe is always the same. Now, for chemists, two important types of energy are chemical potential energy and kinetic energy. Potential energy is energy waiting to happen. Think of a stretched rubber band. If you cut it, all that potential energy gets converted to kinetic energy, ow, which is registered by you as pain. Like a stretched rubber band, chemical bonds also store energy, and when those bonds are broken, that potential energy gets converted to other types of energy like heat or light, or gets used to make different bonds. Kinetic energy is the energy of motion. Now, molecules are always moving. They're not necessarily going somewhere, though they could be, but they are vibrating, stretching, bending, and or spinning. Take methane, which is 4 hydrogens attached to a central carbon, as an example. Drawn on paper, it's just a still tetrahedron. But in real life, it's a jiggling mess. The kinetic energy of molecules is exactly the same type of energy as the energy you have when you're moving around, except that you can be still and molecules can't. If you suck the kinetic energy out of a group of molecules, they'll move less, but they'll never fully stop. Now, in any group of molecules, some will have more kinetic energy than others. And if we calculate the average kinetic energy of the group, we'd have a number mathematically related to temperature. So the more kinetic energy a group of molecules has, the higher its temperature. And that means that on a hot day, the molecules in the air around you are spinning, stretching, bending, and generally shooting around much faster than on a cold day. Now, hot and cold, by the way, are relative terms. They're always used to compare one thing to something else. So on that hot summer day, the air molecules have more kinetic energy than the molecules in your skin. So when those air molecules crash into you, they transfer some of their energy to the molecules in your skin, and you feel that as heat. On a cold day, the air molecules have less kinetic energy than the molecules in your skin, so when you crash into those air molecules, you actually transfer some of your kinetic energy to them, and you feel that as cold. You can trace the path of energy around you. Try it at your next cookout. You burn charcoal, and the release of that chemical potential energy shows up as extreme heat and light. The heat then makes the molecules of your burgers, your hot dogs, or your vegetables vibrate until their own bonds break and new chemical structures are formed. Too much heat and you have a charred mess. Just enough and you have dinner. Once in your body, the food molecules in your delicious or charred dinner get broken down, and the energy released is used to either keep you alive right now, or it's stored for later in different molecules. As night falls, the hot summer air cools, and the flow of energy into you slows. Then, as the air reaches your skin temperature, for the briefest of moments, the flow stops. And then it starts up again in the opposite direction as energy leaves the warmer surface of your skin to return to the universe around you. That energy neither created nor destroyed, but ever shape-shifting, the chameleon phoenix of our physical world.
All right, so hopefully you found that somewhat interesting. So that was a little different take on energy, kind of going back to some of the things we learned about early on, and kind of a good review. So we are adding into this kinetic and potential energy. That's kind of where we're going to be going this week and next week. But the portion that talked about thermal energy was a review, since we've already learned about that. But remember, in a system, energy is neither created nor destroyed. It only changes form. So that brings us to the lab that we are going to do today. So I'm going to go ahead and open the lab up here and kind of give you guys some instructions on what to do, and then we'll break for class and you guys can finish working on the lab, and I'll be able to address any other questions you have about class today. So let's take a look at the virtual lab here. So I'm going to click on this link and it's going to pop up. Follow the instructions in the attached Google Docs. This assignment has 2 parts. So what I've done is when you look at it, there are two things here. The first says part 1, this one says part 2. Part 2 is going to be you creating a graph of what you observed in part 1. So you're still using the same lab and the same activity to address what's in part 2. So let me open this up and show you guys what it looks like. So when you open up the Google Docs, and this should also be posted in the classes for those of you who are at home right now, those of you who are on quarantine. So even if you're in 3rd period, 1st period, 5th, 6th, whatever, these should be available in those folders. So when you open this up, it says the masses and springs, and this is going to relate to us potential and kinetic energy and how that relationship changes. So I'm going to go ahead and copy the link here, and I'm going to get ready to open that up in another tab. Give me just a minute to transition over here. So when you open the link, there's going to be a couple things pop up. Let me go back into sharing really quickly so that you can see my screen. When it opens up, make sure that you click the one that says energy, because that's the one that we're going to be focusing on. So we're going to click here. So this is what you're going to see when the lab first opens up. As you work through the lab, you're going to manipulate what you see here and make observations and answer the questions in the lab handout. So it tells you right here, select energy. We've done that. Set mass to maximum, set damping friction to none, and click slow on the bottom. So I'm going to go ahead and show you what these steps look like. So mass to 300 grams, damping to none, and slow on the bottom. So here's the mass button. So you're going to increase that to 300 grams. Slow down here, and damping is none or to 0. After you've done that, the next job is to attach the mass to the spring. And then you're going to observe the changes. So as you do this, you're going to answer the questions. So for example, where's the kinetic energy the highest? Where's the potential energy the highest, etc. And you can highlight which one of these. So you're going to work through the lab and answer these questions. Once you've done it for the first scenario, you then scroll down and change it to this. So it says reset the mass, and then you're going to change the damping to what's called lots, and that basically represents friction. And then you're going to scroll through and answer. So let me show you what it looks like the first time around. So 300 grams, damping to none, slow. If you want, you can turn these on so you can see, but you don't necessarily need them. So once you've done that, you're going to pick the spring up and connect it and just let it go. So what do you notice is changing as the spring goes down and then goes back up? Look at the chart over here. So you should be able to make some observations about what's happening. You can see kinetic energy in green, potential energy in blue, the total energy in the system, and you can observe what happens. So you're basically going to go through what the lab asks you to do and observe the relationship between kinetic and potential energy, what happens when the mass is different, what happens with the damping is different. Once you have answered this first portion here, 1 through 9, you're then going to go back into Schoology and click on the second document, Kinetic and Potential Energy Virtual Lab Part 2. This section has you creating a graph in Google Slides. I'm going to show you what that looks like. So it opens up, there are 4 slides. The first slide says, once you have performed the lab described in the Google Doc assignment, use what you observed to complete the questions in slides 2 through 4. To display the data on the graph, you will use the insert shape icon on the toolbar. So what you do, and this is my example here, the graph is just the background, the picture is the background pulled from the lab that you guys are working on. Then you will insert the bar graphs of a certain color, depending on kinetic or potential energy, to represent what you observed. And each of these has a question. So it says here, draw the bar graph energies when the mass is at the top. So what did it look like when the mass was at the top of that spring? What did it look like when the mass was halfway down? And then lastly, what did it look like when the mass was at the bottom? So for you to get those bars in here to represent your data, you just go to Insert, Shape, and then you can go from there. See right here, Insert, Shape, use one of the squares or the rectangle here, then you can stretch it, make it shorter, you can change the color. So this is kind of like your version of graphing the assignment. But all the information comes from the same lab that we did here. So as you can see, that spring is still going. If you want to look closely at it, let's say you want to see the halfway mark, you can pause it. So this is about halfway. Well, maybe a little bit more than halfway, but you can play again. You want to see what it looks like at the top, pause it. There it is at the very top. Halfway maybe, and then push play and you can see at the very bottom. And you can see what's happening between kinetic and potential energy. So this is all I have for you guys to do today. Once you have finished this lab, you need to make sure that you submit. All students are doing a lab today, whether you are in class or you are virtual, okay? So if you are at home quarantined or you're in fourth period virtual, you need to work on this lab, answer the questions, and then submit your work. So I'm going to stop sharing and I'm going to come back to you guys. Okay. All right. So does anyone have any questions about the lab today? Any questions about the lab activity or what you need to do? If you don't have any questions about the lab, then you guys can go ahead and sign out of the WebEx. Make sure you work through the lab and you submit it. That's your assignment today. Make sure that you have any makeup work completed. Bye, you guys. If you have anything else you need to get done, make sure you take care of that. If you want to retake a test today, you may retake the test today. So if you are waiting on retaking a test, you can go ahead and do that today. You're welcome. Okay, so if you guys don't have any other questions, you're good to go. Have a great day, and I'll see you in class on Monday.